All right. Welcome back, everybody. I believe I am actually unmuted this time, which is good, so we won't miss the first 5 minutes of video. I want to talk a little bit about what I did last time and what I did over the course of the last couple of days, just cleaning some stuff up. Um, we got to the point where, let's see, what was happening? A couple streams ago, we were implementing jump, and we were jumping around, and we found out that our implementation of the program counter was faulty, or yeah, the program counter. The assembler, uh, yeah. Let me actually just go ahead and show the code here because I think it'll be easier to understand. Let's see. That's tic tac toe. It's been a while. Let me get my bearings. Source tic tac toe. All right. Um, so the in reality, the memory for the program that is loaded into it is 4 kilobytes, and it is from address 1000 to 1FFF. So I was treating it that way, but it turns out that there's a little bit of um, convention in Atari 2600 games to stick the program code at F000, which seems like it would be wrong, but it's not because the memory is mirrored many times over. So um, we've talked about it before, but the 6502 can address 16 bits. The Atari addresses 13 bits, and the way they get around this is that they basically just mirror 8K over and over again. So you can access the same program memory at FDB9, etc. here, as if it were, as if it actually lived at that address. So basically, the first attempt was kind of a hack to like change the program counter to be in that range, but that's not a good long-term solution. So instead, we implemented a memory map. Let me pull that up. Fun, uh, fun little resource for that, which I will link. Is this blog post where not only does he say what all the bytes do and where they're remapped, but he talks about like what pins need to be on and off to make that work. Right. So here, I think the best example here is for this. This is the whole range, so that's not actually what I was thinking of. Cartridge slot. We can. So the cartridge can also be 2K, and then it's mirrored. Um, but you can see um, that anything with a 1 in the fourth most significant bit ends up being redirected to program counter. That's the easiest case, or program memory. That's the easiest case. And when we get into writing some of the memory mapped hardware, so I also implemented the TIA stuff here, you can see that it's that certain pins are essentially turned off on the TIA chip. So it can, and so if these two are turned off and um, then we know that they're addressing the TIA, and we just care about this bottom uh, byte. And actually, we only care like within that bottom byte, it's mirrored twice, as you can see here. So basically, what we did was with our chip, we implemented index and index mute, so that we could. Here's some tests about it, and actually, let me see if I have my macro set up to run it, or my. Yep. Okay. Um, we can see that we can treat what is actually some discrete hardware map to this riot memory program. as a flat map, so we don't have to worry about where things are reading from or writing to. Um, there's going to be some interesting stuff that happens down the line. Down the line, we're going to have to, like the write to TIA, which we've actually implemented here. This is RAM. We're not implementing read from TIA yet. We're going to run into that. It'll be not implemented, but we are implementing write. And this is not actually how this should work. All of this is addressable from like the first 64 bytes, but it doesn't actually update the state in that when you write it, it does some action, and some of those are really interesting. When you read it, it's like a different pathway through the code. So right now we're sort of ignoring that because I would like to sort of get into some more interesting topics, implementing more instructions and working on timing. But eventually we will have to start working on implementing features for these mapped hardware pieces. So what I'm going to do today is jump back to implementing the subroutine jump and hopefully the jump back. We may have to mess with our indexes a little bit because I think we're going to be doing some writing to the riot, which is the input-output device that's mapped onto into the memory, which we haven't messed with yet. And I think that's it. I have all sorts of ideas about how to like sort of structure this and refactor, but I think I'm gonna just go ahead and implement some stuff and see where my pain points are. So to do that, I'm actually going to bring back a little bit of work that I stashed and see if I can work out the conflicts for it. And then we will move ahead. Actually, let me sort of get our bearings here. So we did all of this stuff. We're actually through all of this, which is just basically setting things up for the first run. And then we're going to jump into this intro assembly program, and I'll show you what that looks like. And we get to here, which is the subroutine jump call. And what the subroutine jump call does is this is a absolute address, so it sets the P key, the program counter equal to vertical sync, whatever address that is, right? Which is, it's just a label in a different file at this point. And then it adds that address to the, it adds this address -1 to the stack. Or is it +1? I'll look at the documentation in just a second. To the stack. Hey, Shy Ryan, how's it going? Yeah, this is definitely Rust. Well, this is not Rust. This is 6502 assembly. Rust is up here. Yeah, honestly, emulators are really great sort of use of Rust. Like integers, it's all moving integers around, at least at this point, and integers are all copy and stuff, so you don't have to worry about like you don't really have to worry about ownership. You can just give references away and stuff, and it just doesn't care. So so it's been fun, but I'm learning. I never really got into Rust testing too much, so I'm learning like how all that stuff works. ToggleBit helped me expect specific panics out of things and stuff like that. Yeah. Have you streamed, Shy Ryan, since the last time I saw you? I saw you were getting a new microphone or something. Anyway, um, so then we just yeah. I keep trying to get one. The headphone one seems to work all right, but yeah, right. Keyboard sounds are a thing. The headphone mic seems to work all right, but I keep trying to order from Amazon, and it's like they keep losing the package. I've ordered 3 times. So this one, it says it's out for delivery today, so I should actually get it today. Um, yeah, Ryan, just to recap, what I'm doing is building an Atari 2600 emulator in Rust. I don't have any graphics or anything right now. I'm just sort of implementing I'm trying to compile my own Atari 2600 game, and I'm just implementing things as I come across them. So right now, we're jumping to a subroutine for the first time, which is like a function, but there's no like uh, arguments to it. Like you'd have to set all that stuff up yourself. Um, but then this pushes. I'll have to look it up, but like I think it pushes low byte to the stack pointer. And then it pushes the high byte to the stack pointer, and then the RTS, which is return subroutine, just pops these off and returns you to this address, like with a little modification. So we're working on that right now. Um, yeah, memory map. I think we've covered everything. So let's show it running. So that's sort of cargo. Actually, we'll do it in the editor. I think I have this set up to here. Okay, map. Oh, I overwrote my key binding. Okay. So this should run. Cool. So it says unknown instruction 20, which we can look up on our handy dandy reference here and take a look at what that is. Hold on, let me find it. That's not it. Here it is. Okay, so this is jump subroutine, and this data sheet tells you sort of everything you need to know. It tells you that jump subroutine is a instruction. The hex value for it is 20, which is what we ran into here. And it tells you that it is 3 bytes long, so it's the instruction and the high and low bytes, and then the timing of it is 6. We're going to get into timing a little bit later. Timing is going to be a fun problem. Everything takes like a different amount of clock cycles, and some emulators can kind of ignore that because a lot of systems like have a screen buffer, and so you can kind of, I mean, you can't really ignore it, but in this case, like our clock cycle on the chip is like directly related to what's called a color cycle on the television adapter. There are 3 color cycles per clock cycle, so the timing is like super important here. Anyway, um, jump subroutine pushes the address of the next operation onto the stack before transferring address -1 of the next operation. Right, that's the weirdness. I'm not sure why this happens. I'm guessing it's something to do with the details of the chip itself. So when you jump, you push the address of the next operation -1, and then when you return back, you return to the address +1. So we actually had begun implementing this, and I'm going to unpop a stash real quick and see if I can get it to, let's see if I can make that work. Stash pop. Yeah, and then there's going to be a conflict in main. Oh, 1 second. Cool. Sorry. What did I do? So my base was this. Oh, right, right. So I'm like, yeah. The change was to the, like, to go through the memory map. There's a little bit of difference in the two. I don't think this is the stash I wanted, so I might need to go to the next one. Because if it doesn't have jump subroutine. Nope, I may just need to implement this over again. Let me get out of here. Let's see what's different. Yeah, this is the wrong stash. Okay, so I can just get rid of this. This is also the wrong stash. I didn't remember. Okay, I don't want to get stuck on this for too long. Get status. Get reset hard. Get stash pop. Does it just do the same stash over and over again? This is me not knowing how to. I shouldn't have used a stash in the first place. Yeah, this is just popping the same stash over and over again. Hard. Okay. Get stash like list. Get stash pop. Let's see what happens for you. This looks like something different. Although it doesn't have what I expected in there. Okay, I've spent too long on this. Declaring bankruptcy. We'll never do that again. Okay. So, let's do this. Let's, these are going to be subroutine instructions. Right. I was in like a weird state here. interesting Rust. Okay, so this is going to be JSR flags. There are none here. And we're going to be matching instruction 20. And this needs to be before the catch-all. That makes sense. And then we'll copy one of these. And I'll do this as JSR. Probably don't need this twice, but it's nice. This is three in width, and the timing is 6. The timing will come into play a little bit later, but we can kind of do what we've been doing. We can pull off a couple bytes. The architecture is little endian, so this is actually low, and this is high. And we need to store the... So on the stack, we need to store the program counter -1. So, and then this is where we're actually going to jump to. So let jump address. So we're just going to shift high over by a byte. So this is going to be a U16 since the addresses are 16 bits. And then we're going to add low. And then it's saying, oh, what are you doing? Make sure that you get everything right, because I don't want to add low to 8 before shifting. So I want to... Precedence is an interesting thing. So what does it say? It's saying this will overflow. Oh yeah, so these need to be... So high needs to be U16, so I can just shift it up. This can be U8. I stole that from a place that cared. This can also be U16 without much trouble. All right, and there we have our jump address. Now we need to get our program counter, because our program counter has incremented to get the instruction. It's incremented to get the low byte. It's incremented to get the high byte. And so we're going to get, and we need to put that, we need to break that up into low and high on the stack. So we'll do ret low equals chip.pc. And we just can, the low is just the bottom of that. I wonder if there's a way to split like a U16 into 2 bytes. Think about that. But for now, we'll just do it the old-fashioned way. And we will shift all that over down a byte. And okay, yeah, I don't need to cast it anymore. And we're going to push those to the stack. So chip.stack. Now I think we may probably want a function to do this rather than doing the implementation details of the stack pushes here, but basically what we should do is push to wherever the stack points and then subtract 1 because the stack goes down. Um, so, are there any books or videos that you can suggest to learn to build emulators other than things like this? I have an electronics background and some of this stuff goes over my head. Oh, let me to build emulators. I don't know. I'm sure there's something out there. I learned mostly. Let me find him. Sorry, I'll post him in the Slack. Ferris builds emulators. This guy does. I mean, this is a similar thing, right? This is a guy building an emulator, but this is a really good. It's a really good resource. He goes through building an N64 emulator, start to finish. The other thing that I would suggest for like a really simple version of this is doing what's called a Chip 8 emulator. There might be some books about it. Guide to making a Chip 8 emulator. I'm not going to link these because I can't attest to any of these. But Chip 8 is like a not real. It's like a made up machine architecture that is like pretty simple that you can like that people have built games for and stuff. So it's like the very bare bones of doing an emulator. And there's a lot of guides out there. A lot of people do it. The other thing that I would say that really helped me, NAND to Tetris, is this. There's a Coursera course for it if you're into that kind of thing. But there's also a book, I think it's called Elements of Computing Systems. And this goes through building a computer all the way from like and or logic gates and like up through like how a chip works, like addressing like how to like hook them up to address memory, how to like build an assembler on top of that, and up through like operating system stuff. I went through the first half of this, and then the second half I kind of dropped off because like it got into higher level programming, which I had already learned. I think the thing is like I think the thing is like all of this is context. None of it's sorry. I'll stop the rant pretty soon. None of it's super hard. It's just like getting your bearings in a world that you may be unfamiliar with. Um, so like watching other people do it, I think is a good resource. And then I'm trying to think what else. Yeah, I don't have great stuff other than just kind of weigh it in. The good thing is like a lot of people are interested in this kind of stuff, and they write a lot about it. I don't know if there's like a good like textbook or something about it. So, um, yeah. So what was I doing? Oh, I was gonna push to the stack. So the stack is actually a pointer, and I think it's actually not stack. I think it's SP into memory. So we're gonna set chip dot dot mmap. I could do this. Indexed by the SP. That should be memory, and should be the top of memory at this point. But and then we're going to, or the highest byte in memory because the stack pointer works backwards. And then we're going to push. I think we push them in the opposite order. So we're gonna. I couldn't find clear documentation for this, but we'll just make sure that we handle it properly on both sides. This could be backwards. And then we're going to do a chip. So we're pushing the high byte in dot sp minus equals 1. Boy, my fingers. And then we're going to do the same thing with the ret low. See, I said as U8. Oh, it's probably precedence again, right? Wants everything in. Whoop. And this is saying mismatched types expected. Right. So this is fine. We just need to do as U16. The stack pointer points to 0 page, so there is no upper byte for that, which is why. And then we need to set chip dot program counter to the jump address. And then we should have just implemented jump to subroutine, and we can take a look at that. I think the most, well, we'll do it the quick version. Let's see what our next instruction is. 8E. I think we did it. So let's take a look at what our next instruction is. Yeah, so it's we're going to store X. That's in that subroutine, and I'll show you where that is. So we jump to vertical sync. We need to go to tic-tac-toe. In vertical sync, we're going to store X to start a timer. So that's where we went. We jumped into the subroutine. We will have to implement STX, I believe, and we'll have to implement writing to this, but we have made it to the next one. And let's take a look at the debug output, since that's super fun. So here it is, setting everything to 0 as it counts up, and then it'll go on, and you can see that the program counter jumped to F0, F8 there at the very end. That is the address of that. It's the address of vertical blank, and it was F0. F8, because the whole program by the assembler is set is aligned to F000. So, and we've implemented that indexing so that you can access that data at any of those indexes. Cool. I'm going to go ahead and commit that, and then we're going to go ahead and do the next instruction, and hopefully the goal here is to get to the return and start talking about timing, which will be an interesting thing. So yeah, that all looks right. I'm going to start naming them so that they're a little more readable rather than just the hex. Cool. So let's do that 8E. Let me find this. Yeah, so it's going to be a lot like store A. Thank you for the follow, Harry88. Welcome to me trying to implement a Atari emulator. Um, it's been fun so far. It's going to be something close to this. We're going to kind of keep them together. I need to figure out how to make this manageable, because there are a bunch of the instructions are grouped together, but there are like hundreds of them, because a different hex code is used for each address mode. So in fact, we're going to see a new address mode here. Quick explanation: the there's a number of address modes. Zero page means that the memory that we are addressing is in the very first 256 bytes of the memory map. So you can send it just 1 byte, and it knows what to do. Zero page with an offset is that same thing, except that it uses the X register, or sometimes they use the Y register, to index into that zero page. So it goes to whatever address you point to and then offsets by that. And then there is indirect, which we haven't gotten to yet, which is dealing with pointers. And then this is going to be absolute. Absolute. And what was this? 0x85. It says it overlaps. Let me see what I can do here. $8E. It's not 85. It's 8E. Cool. And so the that doesn't matter. That's just so this is actually going to be 4444 because this is 2 bytes. And then the width of this is 3, and then the timing of this I believe is 4, but let me take a look right back at that. Yeah, so that takes 4 cycles to execute. And so instead of doing 1 next byte, we're going to do 2 next bytes. Again, it's a little endian, so it's low and high byte. These are going to be as U16, as U16, let adder. We're going to take high, shift it a byte to the left, and add low. That should give us our full address. And then we are going to set that address equal to the X, the value of the X register. So, adder. And that is all there is to it. We will encounter an error, though, which should be fun, and that'll drive out a little bit more behavior. Cool, yeah, so not implemented yet is not implemented yet. So apparently that is not a very good message to have. Let me fix that real quick. Not implemented yet. So this is going to be index not implemented. I can spell implemented, I probably. We'll see if we can print out our instructions. I'm not always sure which macros take format arguments, so hopefully it'll work. What do you think, Rust? Do you like that? Rust likes it. It's good. And we'll do the same here. Not implemented for X. So it should then see a better message when we run this. That's the test. There's okay. Test pass. Good. That's good. Index mute not implemented for 296, right? So we can go take a look at our handy dandy guide on mapping on the memory map, and we'll see what's going on here. So I did do that in X hex, right? So it should be, yeah, okay. Okay. So 296, let's see. So, this may be a little busy for us. Let's go look at a different version of this that's a little less busy. So we see, yeah. So we're in Riot addresses which are 0, 0 through 1F, and we can go take a look at this other guide, 29F. So basically what this is doing is setting a timer. I can do a quick search for timer in here. Timer functions. So it's actually saying, yeah, so it's actually saying it's mirrored somewhere else. 29.8 through 29B. 2.8. Oh, interesting. Two 9F. Yeah, there it is. Enable the timer interrupt and set the timer using a 1024 cycle interval. So basically the Riot chip has all the input and output stuff, including timers. So when you set this, you set it to, and let's look at our code real quick, because this will be a little bit, this will eliminate some things. It's in vertical sync. So we're storing the value of X, which is hex. That might just actually be a straight 49. I believe it's straight 49. So this actually is like a very long timer, and this is going to go off at the beginning of the frame. So we are setting that to whatever the value of X is. So I think this is actually like decimal 49 to times 1024 in this case. I was saying 64. Did I get the wrong one? 9.6, not 9F. Okay, that makes sense. I was like, that's a really long time. Let's take a look at our 9.6, right? 64. So 64 times 1026, or 10. 64 times 49. I don't know where the 1026 came from. And right now we're not kind of worried about timing. We're sort of glossing over that. So basically all I need to do is on the chip, I'm going to basically do this over again, but for the Riot. And we'll worry about timing later. Actually, we'll get to timing pretty soon because we eventually wait for that timer, so it'll have to work. But I think we can go right now. So let's see. Right. And we'll have to do the same thing here. When you read, you get the state of the of the hardware. When you write, you actually like do something, but should affect the behavior. All right. Okay. And then we'll go take a look at what we were just looking at. Not that one. And it'll show us what the pins are here. So we'll just copy that over. This will be an interesting one. You can see some of them are set and some of them are not. Oh, this is interesting. Like you have to have a 1 in here. We may just fudge this a little bit. So that should be a 32. It's not a very big address space. So, let's see. I think we only. Yeah, see, we're getting like into some details here, and I don't timer interrupt flag, so I don't really care about most of that. So Riot's IO functions timers. Read the Riot RAM. However, Riot's IO timer function don't use all 7 address pins. So for now, we're going to just implement the whole thing. I think this will work. Let's just write our test cases. So the first address, and we'll just use this simpler version to look at where we should see those addresses. So at the 2829F, so we'll just I think that's right. Yeah. And those are from 0 to 1F, right? Okay. We'll just start with that and do some mirrors later. Yep. So it's saying the index mute is not implemented for 290, which makes sense. So we're going to do index mute. This is TIA. This is memory. And this is going to be Riot. And we'll have to figure out what exactly we're going to have to do here to make that work right. So, copy that. So we can take a look at it. All right, so it's saying if these things are set, does that make sense? 0 to 80. So right, so okay, yeah, 2 is there, so it'll also be at so okay, we can go through these one at a time. So this on the 13th bit here, um, is whether it's in program memory. If it's one, it's in program memory. If it's 0, it's in this like lower sort of range with the TIA and the main memory and all that stuff. So then we come down here to uh, in this case it's 2, but other valid options uh, would be what is that 5 would be boy um, 4 8 8 plus 4 plus 1 or no, that's not 5. That's 6, I guess, and then right 4 plus 2, yeah, 6. So 8 plus 4 plus 2 is yeah. So anyway, I think I've got that right. So we just need to mask this out, and this is going to be one of something a little more like this because we have both bits we need on and off. We want to go with off first, so it's just this one, and this says, is it lower? We probably are handling that since we're grabbing everything that's not like that here, but it's nice to do it explicitly. Doesn't it like, okay. And then we need these turned on, which is going to be it's going to be 4 here, 8 here. I think that, unless I'm missing something, that is correct. Okay, and then we're going to do riot, and then we're just going to mask out definitely might have something wrong here, but I think we just need the bottom. I guess I didn't save my changes here. Okay. That was a small change that I apparently just lost. All right, so I think we only need yeah, these are all mirrored, so we only really need this is RAM. I think that other sheet had a better thing for 0 to 1F. Yeah, and then everything's repeated from there. So that is actually this. So for instance, 80 is 1, 0, 0, 0, 0, 0, 0. So we can ignore this one. And then 1F is 1, 1, 1, 1, 1. So 80 to 1FF. 180 to 1FF. So that's this. But I think in both cases we can just ignore everything because the max we need is actually this. So I think we can just AND it with 1F and that'll work. Then we write our tests. run our tests. Didn't know what a right is because I did something very wrong. Spelled it wrong, and it told me, but I didn't pay attention. Okay, so that works for now. Let's take a look at some of the mirrors here. Um, we can look at that easier sheet. Yeah, this is going to be a little bit involved to implement when we actually get to doing it, because I think some of the stuff is like mirrored here too, like inside the right addresses. So we're gonna get here. Yeah, let me like validate BFF. Right. Okay. And those are gonna be mirrored a bunch of times. So. Yeah, let's do the mirror up, which is A and B, and see that we made that work. First mirror. Okay, that passes. These have been working pretty well, so I'm just going to skip over. So we did the bottom of this one, like this mirror. So in this next block, we'll do the top address. So that's 3EO and 3FF. Okay, so that worked. So then I think I'm just going to jump up a little bit and make sure that I can do that um, at a higher address range. So let's go like not the end of them, because like a lot of these are. Yeah, we'll just go somewhere in the next address range. Like this is interesting. What about these ones? 2100 and 213F. All right. Right, 2100 and 213F. Okay, so that all passed. So I'm going to say that that worked properly, and we may have just implemented our, we may have just implemented this. Let's see what happens when we run. Oh, that's our tests. Okay, cool. Those still work from just a second ago. And those are tests again, because I keep hitting my muscle memory buttons instead of my... Okay, so it's saying unknown instruction 60, which I believe gets us to the next thing I want to do today. I keep hitting the wrong buttons. Silly Windows. Which is returned from subroutine. So actually, a fun thing. Why don't we modify main. We'll get rid of this. We have a little code that like does some stuff. So we have TIA, right? So we're gonna actually do pretty much all of this again after the TIA. Here, it's a better place to steal it from. Right. And this is going to be right. And then what is one? Why am I unable to think properly here? So the right range is so this is 16 would be 9 and then 32. So it is 32. Okay, so that is what I was thinking. All right, so we're gonna go for why did I do this? I think I did this wrong. So we're going to go the rows are 16 wide. We're going to do that, and then we're going to go to 2. And then see if we... So we get in debug mode if we crash out somewhere. Awesome, yeah, you see the rights here to these. Yeah, cool. I think we got it. So that is straightforward enough. Let us commit that. Kind of two things there, isn't that? But we needed one for the other, so we'll just absolute. And I think the next thing we need to do is actually RTS. So let's take a look at that data sheet one more time. I know I keep switching back and forth here, but oh, I forgot about something for STX. Good catch. Oh, no. Okay, no flags. That's fine. So, JSR, we'll just copy a bunch of this stuff because it'll be important. Or it'll be similar, but like in reverse. So return subroutine. X is 60. I believe the width is 1. And the timing is 6. Let me verify that. Width 1, timing 6. Okay, so we don't need to pull off low and high bytes, but we will need to grab those from the stack. So that'll look something a little like this, but we won't need to set them. And we're gonna add this stack back up. So this is gonna be, so we put them on high first to low first. So this is gonna be let low. Just checking something. Yep, I missed something here. That's really important. I need to subtract 1 from here. Cool. So here we are. Get the high byte back. And then let me make sure that I know what's happening. +1. So we'll need to set this to high shift by a byte plus low plus 1. Found U8. What doesn't it like? Mismatched types. Expected U16. Found U8. So I pulled them off. These need to be as U16. I don't believe I believe the stack pointer is already U16, so that's not. That might be unnecessary. No, right. We talked about that already. Because it's 0 page, so we just need to, okay. Great, and I think that should actually probably do it for us. Yeah, let's see what happens when we run it again. We should get to something completely new, and we'll see what that is. Unreachable. Unreachable. Why? Oh, because we're returning from there. It's still unreachable. Right, this is 60. Surprised it didn't do the overloaded match arms thing. Okay. So then we go here. Unknown instruction CA. Let's see what CA might be. CA is a decrement count, so let's take a look at see if we can find that in our assembly code. So we're returning from here. We're in this intro page, so we're probably going to I vertical blank. Yeah, this is not what I was. This is not what I would expect. I think maybe I'm returning to the wrong place. So let's take a look at that debug mode. So we'd would expect to be... Okay. Yeah, I think we're going to see something really wrong when we do our debug. Yeah, PC 7405 is very, very wrong. So that must be somewhere in this. We know we're jumping to the right place, so this must be something here. Let's do some debug printing. E print line low. High. Low. High. We'll run the fast version. We'll add our semicolons. Right. So that's very wrong. Actually, so we should be able to see when we do the debug what's going on to the stack pointer. I may need to... Oh, the stack pointer... Yep. Pretty easy. I'll wait for this to finish, but you'll be able to see it at the end of the memory. Right? It's 70... Oh, no. It is 74 and 10. Isn't it? So it's something in our jump. We're setting the stack pointer wrong. This is ret low, ret high, and then we'll take a look at the PC. Chip.pc. Do the fast running one. I got it reversed, didn't I? Yes, I did. Okay. How did I do that? Right, I pushed the high. Push the low second. Very interesting. Okay, so my low is 75. That makes sense. My high is 10. Yeah, that totally makes sense because my PC is 1075. And then, okay, so let's look at the debug output again because it will show us what order they're on. At the end of the RAM, that's at the very end of the RAM here, when it gets to jumping to that subroutine, it should be... So it pushes the low byte first, and then the high. No. And then the low. Pushes the high byte first, and then the low. High byte first, then the low. So then I still need to do this though. Yes, I need to, because the stack pointer is in the place where I could write to it, and then I need to increment it to pop back. So that is why I need a functions that are tested for reading and writing the stack pointer. So let's keep this eprint line stuff in here. Take a look at it one more time. So then when we're pushing it, yeah. Yeah, and you're going to see that there's two, like, it comes back. A5 is the next instruction that it runs into. Let's see if that's a little more reasonable. Load A. It's not what I thought it would be, but source, tic-tac-toe, .dasm. We want actually intro. Ah, yeah, okay. So yes, load A is this instruction right here. Okay, that was fun. I think this is going to have to be a short stream today, so we will find somebody to raid. But let's just take a quick review of what we did today. We implemented a couple of things, but mostly we implemented jumping to, or a subroutine, jumping to a subroutine, and then returning out of it. And then we did this store X with absolute addressing, which is setting a timer in the Riot chip. We added to our chip the ability to index, or to set these things for Riot. We'll take out some of this. Don't need it anymore. And with a big to-do caveat that this shouldn't actually just set some memory, it should do something. So let me commit. Yeah, that's good. That's good. Make sure everything. So that's the -1. That's the +1 on the other side. Return subroutine. Let's make these commits look somewhat nice. Cool, and that stuff's in the Git repo, and this video will be up on YouTube later today for anybody who wants to review it. I'll try and make sure that we get all the resources, the named Tetris and stuff like that in there. Let me find somebody to raid.